Students, with respect to resonance concepts, in the previous sessions, I discussed about some introduction, and I started series resonance, that is resonance in series circuits. All these points in detail that I already discussed. Who are not attended, you please go through these points. I calculated at what frequency voltage across the capacitor is maximum, at what frequency voltage across the inductor is maximum. Then I drawn the characteristics, and I given what is the quality factor. All these points already completed. Who are not attended, you please go through these points. Then I derived the formula for bandwidth. Bandwidth equal to F2 minus F1. This is one formula. Omega 2 minus omega 1. If you write in terms of angular frequency, we got the R by L. If you write in terms of the frequency, we got F2 minus F1 equal to R by 2FL. That is, we know this omega 2 minus omega 1 is equal to R by L. That this is the equation 1. And we know that omega naught square equal to, that is omega 1 into omega 2 equal to omega naught square, that equal to 1 by LC. Once you know the omega 2 minus omega 1, how to write the omega 2 plus omega 1, students? Then omega 2 plus omega 1 equal to, that is, if you know the A minus B, how to write the formula for A plus B? Square root A minus B whole square plus 4AB. Then you can get A plus B now. Same I am applying here. Omega 2 plus omega 1 equal to A minus B is the omega 2 minus omega 1. That is R by L whole square plus 4AB, 4 into omega 1 into omega 2. Omega 1 into omega 2 is 1 by LC. That this is the equation 2, students. Then by solving 1 and 2, that is A plus B and A minus B now. By solving those two equations, we can get expressions for cutoff frequency. That is by solving 1 and 2. By solving 1 and 2, we can get what is omega 1 and what is omega 2, students. These are the expressions for cutoff frequencies. But directly I am writing, by solving 1 and 2, we can get omega 1 equal to minus R by 2L plus square root R by 2L whole square, R by 2L whole square plus 1 by LC. What is omega 2? That is R by 2L, omega 2 equal to R by 2L plus square root R by 2L whole square, R by 2L whole square plus 1 by LC. These are the expressions for cutoff frequencies. This is the expression for which one? Lower cutoff frequency. This is lower cutoff frequency. Lower cutoff frequency. Then this indicates the upper cutoff frequency. This is upper cutoff frequency. Cutoff frequency. These are the expressions for cutoff frequencies. That is the lower cutoff frequency and the upper cutoff frequency. You have to write this omega 1 equal to 2 pi f1. From this you calculate f1. You write omega 2 equal to 2 pi f2. From this you have to calculate the f2 steps. This also you have to consider. What the bandwidth expression in terms of angular frequency? What the bandwidth expression in terms of the frequency? And this is the lower cutoff frequency. This is the upper cutoff frequency. And one more important observation that I have to explain here. You have to concentrate. Yes, friends. Very important observation here. Let this bandwidth, this is the bandwidth that all of you well know this. This is the bandwidth. Okay. This is bandwidth. And this is omega 1. And this is omega 2. and this is omega naught. If this total is bandwidth, you have to take this is the half of the bandwidth, that is bandwidth by 2. This also half of the bandwidth, that is the bandwidth by 2. Now what is the observation here? This is omega 1 means, concentrate friends, this is omega 1 now. That is up to this omega 1. This is omega 1. And this total is omega naught. This is omega naught. And this is omega 2. This is omega 2. Then what is the observation here, friends? If you have to calculate omega 1 in terms of bandwidth, omega 1 in terms of bandwidth, from total omega naught, from this omega naught, to subtract this, we can get omega 1. This is omega naught now, but I have to calculate this one. Then from this omega naught, to subtract this term, then we can get omega 1. This bandwidth and cutoff frequencies. I am writing the cutoff frequencies in terms of bandwidth. What is omega 1, friends? Omega 1 equal to, this total is omega 1 now, this is omega 1. This is bandwidth by 2. Then from this omega naught, you subtract this value. Then we can get omega naught minus bandwidth by 2. Omega 1 equal to omega naught minus bandwidth by 2 is also equal to omega naught minus, what is bandwidth? The calculated bandwidth equal to R by L. This is equal to R by L, then R by 2L. Yeah, this is one formula for omega 1. That is the cutoff frequency in terms of bandwidth. You can also write like this now. 2 pi f1 equal to, this is 2 pi f0 minus R by 2L. From this, what is f1, friends? Yes. Bandwidth equal to this bandwidth. Or we can write three equations, these three terms at a time. Shall I write like this? 2 pi f1 equal to 2 pi f0 minus bandwidth by 2 is also equal to 2 pi f0 minus R by 2L. From this, what is f1, friends? Bring this 2 pi this side. f0 minus bandwidth by 4 pi, it is also equal to f0 minus R by 4 pi L. This is the expression for cutoff frequency. Cutoff frequency in hertz, cutoff frequency in radian per second. This is the calculation of cutoff frequency in terms of bandwidth. Similarly, can you calculate what is omega 2? Is omega 2 equal to, from this point to this point, omega naught, and this is bandwidth by 2. Omega naught plus bandwidth by 2 is omega 2. Then what is omega 2, friends? Omega naught plus bandwidth by 2 is also equal to omega naught plus, for the bandwidth, R by L, that is R by 2L. You can write from this what is 2 pi f2 equal to, this is one expression. I am writing cutoff frequencies in terms of bandwidth. 2 pi f2 equal to 2 pi f0 plus bandwidth by 2, this is equal to 2 pi f0, this is equal to 2 pi f0 plus R by 2L. From this, how to write what is f2 equal to? f2 equal to f0 plus bandwidth by, bring this 2 pi this side, 4 pi, that equal to f0 plus R by 4 pi L. So this is the calculation of f2. I am calculating cutoff frequencies in terms of bandwidth. Angular frequencies, frequency, angular frequency, frequency. Yeah, this observation is also important. Clear? This is about bandwidth and cutoff frequencies. That is how to concept. Very important formulas that I given here. Before this, we have to add the one slide. Just a minute, I'm adding the slide. Yes. Just for quick reference, this once again I'm giving students. Note points mainly how to concentrate. We know this omega naught equal to square root omega naught equal to square root omega 1 into omega 2 f naught equal to square root f1 into f2. Next, bandwidth equal to bandwidth omega 2 minus omega 1 that equal to r by l. Bandwidth equal to f2 minus f1 that equal to r by 4 pi l. Every formula is important. Already questions are framed in combinations. R by say 2 pi l or 4 pi l. See the 2 pi l now. It's r by 2 pi l. Next, third write omega 1 equal to omega naught minus bandwidth by 2. And also write f1 equal to f naught minus. But write f1 equal to f naught minus r by 4 fl 4 pi l r by 4. That is omega naught omega 2 equal to omega naught plus bandwidth by 2. And also write f2 equal to f naught plus r by 4 pi l. You can also write cutoff frequency omega 1 equal to minus r by 2l square root r by 2l whole square plus 1 by lc whole square plus 1 by lc. You can also write omega 2 equal to r by 2l plus square root r by 2l whole square plus 1 by lc r by 2l whole square plus 1 by lc. Okay, this one small. Next, what are the power factor at cutoff frequencies? In series resonance circuit, what is the power factor at cutoff frequencies? How to calculate the power factor at cutoff frequencies? Students, we know that the impedance Z equal to R plus J into omega L minus 1 by omega C. R plus J into omega L minus 1 by omega C. And this observation already given at omega equal to omega 1 XC greater than XL. XC greater than XL. At omega equal to omega 1 XC greater than XL. Then omega 1 L minus 1 by omega 1 C is equal to minus R. Then Z equal to R plus J into third substitute omega 1 into L minus 1 by omega 1 into C. This is equal to R minus JR. Then Z equal to R minus JR. Z equal to R minus JR. R minus JR. Z equal to R minus JR. Then you have to calculate what is the power factor at cutoff frequency omega 1. Power factor at omega equal to omega 1. That is at a cutoff frequency omega 1. What is the power factor? It's R by Z now. R by Z. Then R by square root R square plus R square. This is equal to how much we can get? 1 by root 2 R. That is 1 by root. That is 0.707. Friends, we are getting 1 by root 0.707. So 0.707 is lagging or leading. XC greater than XL now. At cutoff frequency omega equal to omega 1. Sir, at omega equal to omega 1, how it is XC greater than XL? Please go through the previous explanation. The previous sessions that I given this explanation. Then 0.707 leading. At omega equal to 1 by root 2 0.707 leading. Then what about the angle? It's a leading angle now. 1 by root 2 cos pi. Power factor is cos pi. Cos pi equal to 1 by root 2. Then pi equal to 45 degrees. Is it plus 45 or minus 45? Plus 45. Why? The current is leading. In leading power factor means current is leading. Then we are measuring the angle in anti-clockwise direction. The angle is measured in anti-clockwise direction. Plus 45. The angle is measured in clockwise direction. It's a minus. At this point is already given. That's why angle is plus 45 degrees. What about at omega equal to omega 2? At omega equal to omega 2, you know that XL greater than XC. If XL greater than XC, then omega 2 into L minus 1 by omega T into C equal to plus R. Omega 2 into L minus 1 by omega 2 into C equal to plus R. Then from this, what is the Z equal to? R plus J into omega 2 into L minus 1 by omega 2 into C. This is equal to R plus JR. Then what is the power factor? This power factor at omega equal to omega 2 cutoff frequency, or the cos pi equal to r by z, r by square root r square plus r square students. R by square root r square plus r square. They are getting 1 by root 2. It is 0.707 lagging. Why I am taking it as a lagging? XL greater than XC. That's why it is a lagging. If it is a lagging angle, then you have to take the angle is minus 45 degrees. Yeah, these are the calculation of power factor at cutoff frequencies. What is the power factor at cutoff frequencies? At lower cutoff frequency, power factor is 0.707 reading, reading angle is plus 45 degrees. At upper cutoff frequencies, 0.707 lagging angle is minus 45 degrees. This is for upper cutoff frequency. This is for lower cutoff frequencies. The question is asked at lower cutoff frequencies, what is the power factor? 0.707 leading. At upper cutoff frequencies, what is the power factor? 0.707 lagging. At lower cutoff frequencies, what is the power factor angle? Plus 45 degrees. At upper cutoff frequencies, what is the power factor angle? Minus 45 degrees. This points also you have. One more observation is relation between quality factor and bandwidth. What is the relation between the quality factor and bandwidth, friends? I think all of you know this. What is the relation between quality factor and bandwidth? We know this. What is the formula for quality factor? Quality factor equal to, you know this one. Quality factor formula. Quality factor Q equal to omega naught into L by R. Can you write what is the relation between quality factor and bandwidth? Can you try this? Try. Yes, friends. So we know that quality factor equal to omega naught into L by R. Shall I write like this? Omega naught into this L I am bringing into the denominator, that is R by L. You know this formula, no? Bandwidth equal to omega 2 minus omega 1, that equal to R by L. This formula already derived. Then quality factor equal to omega naught by, what is R by L? R by L is the omega 2 minus omega 1. This is equal to omega naught minus bandwidth. This is the formula. So this is the relation between quality factor and bandwidth. Quality factor equal to omega naught by bandwidth. That is, quality factor is inversely proportional to the bandwidth. Quality factor is inversely proportional to the bandwidth. We can also write this formula 2 equal to 2 pi f naught by 2 pi f2 minus 2 pi f1. Take 2 pi is common, cancel, but you can get f naught by f2 minus f1. Even f2 by f2 minus f1 is also bandwidth. That is, quality factor equal to f naught by bandwidth. Quality factor equal to f naught by bandwidth. But the only difference is omega 2 minus omega 1 equal to r by L. Na? This is the bandwidth. But here, to write bandwidth equal to f2 minus f1, that equal to r by 2 pi. If you substitute f2 minus f1, bandwidth is r by 2 pi. If you substitute omega 2 minus omega 1, you substitute bandwidth equal to r by L. That only difference. That is, quality factor equal to resonance frequency by bandwidth. And quality factor equal to resonance frequency by bandwidth. Resonance frequency by bandwidth. That is, what is the observation here? If the band quality factor is increases, bandwidth is reduces. Quality factor is increases now. If quality factor is increases means what the bandwidth reduces. Quality factor increases, bandwidth is reduces means we can get the curve like this. It's a narrow curve. It's a narrow curve. That is, high Q coils are having narrow curve. High Q coils, high quality factor coils are having narrow bandwidth. high quality factor coils are having narrow bandwidth. Yes. If quality factor is reduces, if quality factor is reduces, what of the bandwidth increases? Then low Q coils are having wide bandwidth, wide bandwidth, low quality factor coils. Then if you draw the characteristics, we can get the characteristics like this. This is for low quality factor coils, large bandwidth. The high quality factor coils, small bandwidth. Then narrow curve, and this bandwidth is more width we can get. But this is narrow, this is wide width. That is how to consider. So these are the relations between quality factor and bandwidth. Relation between quality factor and bandwidth. All these points may be wrong. That is quality factor and bandwidth is inversely proportional. Quality factor and bandwidth is inversely proportional. Next, one more important relation that you have to concentrate: selectivity of a network and selectivity and relationship between bandwidth, selectivity, and quality factor. This formula is also important. Relation between bandwidth, selectivity, and quality factor. Bandwidth, selectivity, and quality factor. Here, selectivity in the sense narrow range or wide range of frequency. If you have to go for narrow range frequency, that is, you have to select the coil. Is it for narrow range frequency or wide range of frequency? For narrow range frequency, you have to select the high quality factor coil. For wide range frequencies, means bandwidth is more, then you have to select the low quality coil. Then selectivity of a network is ability to discriminate or distinguish between desired and undesirable frequencies. Selectivity of a network is the ability to discriminate or distinguish between desired and undesirable frequency. Then which frequencies you have to allow, which frequencies you don't want to allow. Yeah, that is nothing but a selectivity. In general, the selectivity equal to this important formula. How to write the selectivity S equal to F naught by F2 minus F1. This is the formula for selectivity. F naught by F2 minus F1. The selectivity equal to F naught by F2 minus F. Then what is selectivity equal to? F naught by bandwidth. F naught by bandwidth. Selectivity equal to F naught by bandwidth. Okay. But you know the relation between bandwidth and quality factor na? Then quality factor equal to F naught by Q. That is quality factor equal to F naught by bandwidth na? Then F naught by bandwidth is nothing but which one? Quality factor. F naught by bandwidth is nothing but a quality factor. This is F naught by F2 minus F1. This is equal to quality. That is S equal to Q, that equal to F naught by bandwidth. What are the observations, friends? If quality factor is increases, then what the selectivity is also increases. Then what the bandwidth reduces. Then you have to use for narrow range frequency. Narrow range frequency selection. If quality factor is reduces, what the selectivity? The selectivity is also reduces. But what about the bandwidth? Increases. Then this is used for wide range of frequency. Wide range of frequency. This is about the relation between bandwidth, selectivity, and quality factor. How the frequency selection depends on quality factor and bandwidth. And one more important is, which is repeated. One more important is how to concentrate relationship between quality factor and damping ratio. Relationship between quality factor and damping ratio. This already completed. Adding one more factor here. Just a minute. I'm adding the slide. What the relationship between quality factor and damping ratio? Between quality factor and damping. Yes. Let's consider a series RLC circuit. This is the series RLC circuit. We are given the AC supply voltage. This R, this is the L, this is the C. Friends, for RLC circuit, you know the characteristic equation. For RLC circuit, what are the characteristic equation? The characteristic equation. The characteristic equation is S square plus R by L into S plus 1 by LC equal to 0. Think all of you know this now. S square plus R by L into S plus 1 by LC equal to 0. When in control systems also study this. This is the characteristic equation. And I am comparing with this second order system equation. S square plus 2 zeta omega ns plus omega n square equal to 0. From this, what is omega n equal to? That is omega n square equal to 1 by LC. Then what is omega n? This is the natural frequency of oscillations. That is 1 by root LC. The natural frequency of oscillations equal to 1 by root LC. Natural frequency of oscillations equal to 1 by root LC. Then what is 2 zeta omega n? 2 zeta omega n equal to, this I am comparing with this R by n. Then 2 zeta into, what is omega n? 1 by root LC. 1 by root LC equal to R by LC. 1 by root LC equal to R by. Then from this, you have to calculate the, what is zeta? That is the damping ratio. That zeta is the damping ratio. Zeta equal to damping ratio. Based on this ratio only, then the oscillations in the system will depend. The oscillations in the system will depend on the damping ratio. Zeta equal damping ratio. This is equal to root L cancel. We can get R by 2 into root C by L. Root C by L we can. Then damping ratio zeta equal to, that is 1 by 2 into R into square root C by L. Zeta equal to R into square root of C by L. You can also write like this. 1 by 2 into, shall I write like this, friends? 1 by R into square root L by C. I am bringing this R into the denominator, 1 by R. This also I am bringing into the denominator, root L by C. Again, if you bring this here, R. If you bring this numerator, root C by L, you can do. Then this is equal to 1 by 2Q. What is Q here? 1 by R into square root L by C. This formula starting I given. The quality factor, one more formula is 1 by R into square root L by C square. So this is the damping ratio and the quality factor relation. Very important. Then damping ratio equal to, damping ratio zeta equal to 1 by 2Q. This is equal to 1 by 2Q. So this is the damping ratio for. Then what is the observation here? You know Q equal to 1 by 2 zeta na? You know Q equal to 1 by 2 zeta. That is quality factor equal to 1 by 2 zeta. Friends, all of you know this for critically damped. What is the zeta? For critically damped case, what is the damping ratio? Very good. For critically damped case, zeta equal to 1. Zeta equal to 1. What is the quality factor equal to 1 by 2? Zeta equal to 1. The quality factor equal to 1 by 2. That equal to 0.5. For a overdamped system, for overdamped, this observation is important. For a overdamped system, friends. For a overdamped case, what is zeta greater than 1? Zeta is greater than 1. What about the Q? Zeta is greater than 1. Then Q we can get less than 1. Q equal to 1 by 2 zeta now. If zeta is greater than 1, then Q is less than 1. For underdamped case, friends. For underdamped system. For underdamped system, zeta less than 1. Then what is Q equal to 1 by 2 zeta? Then you can get Q is greater than 1. Okay, these are the relations between quality factor and the damping ratio. And one more point to remember, whatever the resistance designed for the critically damped system is called critical resistance. The resistance designed for critically damped system. See, every observation is important. You please once again practice. The resistance designed for critically damped system. Critically damped system, yes, is called critical resistance. Is called critical resistance. Whatever the resistance designed for critically damped system is called critical resistance. Resistance designed for critically damped system is called critical resistance. Then we know this for critically damped system, Q equal to 1 by 2. What is the Q formula? Q formula is 1 by R into square root L by C equal to 1 by 2. From this, what is R equals, friends? R equal to 2 into square root L by C. 2 into square root L by C. This is called critical resistance. The resistance designed for critically damped system is called critical resistance. That is R equal to 2 into square root L by C. R equal to 2 into square root L by C is the critical resistance. But point to remember, if R equal to, if you write R square, if you write R square equal to 4L by C, now this is called critically damped. One more condition for critically damped. This you studied even in the control systems also. R square equal to 4L by C, that is the critically damped. So R square greater than 4L by C, sir. To write like this, this is the over damped. Very important. R, even who are electrical students are there, this is useful even in power electronics also. R square less than 4L by C, that is under damped. R square equal to 4L by C, critical damped. R square greater than 4L by C, over damped. R square less than 4L by C, under damped. Okay, these are the relation between damping ratio and critically damping ratio and quality factors. With this, the different concepts with respect to series resonance is completed. I given so many concepts with respect to series resonance, friends. All these points you have to concentrate. The starting from every observation is very important. All these points with respect to series resonance only. I started with the resonance in series circuits. I given the condition for series resonance circuit. How this reactance, resistance and capacitive reactance, inductive reactances are varying with respect to frequency. And what is the variation of I and Z with respect to frequency? Variation of I and Z with respect to frequency. What is the variation of power factor with respect to frequency? How the power factor is varying with respect to frequency? At what frequency voltage across the capacitor is maximum? At what frequency voltage across the inductor is maximum? And I given the characteristics also. This characteristics also you have to concentrate. Then after this I started what the quality factor. I define the quality factor of various types of coils. And what is the voltage across the inductor and capacitor at resonance condition? What are the bandwidth and cutoff frequencies? Very important observations. I given so many relations of bandwidth and cutoff frequencies. What are the power factor at cutoff frequencies? What are the relation between quality factor and bandwidth? What is the relation between bandwidth, selectivity and quality factor? What is the relation between quality factor and damping ratio? What are the observations from this damping ratio, friends? All these you have to consider. Then before starting the one more concept in the resonance, that is the resonance in parallel circuit. You have to see some practice questions with respect to series resonance. That is the resonance in series circuits. Just a minute, I am adding the. Yes. In RLC series circuit, P equal to 10 sin 2t and R equal to 5 ohms, L equal to 0.5 Henry. What is the value of C so that current I is in phase with voltage? Voltage. Just a minute, please write. What is the answer, friends? Current is in phase with voltage, means it indicates the resonance condition. Correct or not? Current is in phase with voltage now. Current is in phase with voltage. Even current I is in phase with voltage. In phase with voltage. That is, voltage and currents are in phase. If voltage and currents are in phase, then it indicates resonance condition. Resonance condition. RLC circuit now. RLC circuit. In RLC circuit, current I in phase with voltage, resonance condition. Resonance condition is omega naught square equal to 1 by LC. But what is the frequency here? 2 radians per second. Substitute here 2 square equal to 1 by how much inductance? 0.5 into C squares. Then what is C equal to? 1 by 4 into 0.5. This is equal to 1 by 2. This is how much you can get? 0.5 farads. Or you can also write like this. At resonance, you can also solve like so many methods are there. XL equal to XC. Omega naught into L equal to 1 by omega naught into C. Then 2 into L equal to 1 by 2 into C. What is L? L equal to 0.5. From this, what is C equal to? 1 by 2, 0.5 farad. Like this also you can solve, sir. Formula you have to apply. But condition is, this indicates at resonance condition. How to identify it is a resonance condition? In RLC circuit, not in every circuit, sir. In RLC circuit, if the voltage and currents are in phase, that indicates the resonance condition. Next. Can you try this? For the circuit shown in figure, if XL equal to XC, the values of R, L, C respectively. For the circuit shown in figure, if XL equal to XC, the values of R, L, C respectively. XL equal to XC means this is at what condition? Resonance condition. Is that a resonance condition? Yes. Students, we know this. At resonance condition, at resonance, XL equal to XC na, it's a resonance. At resonance condition. Sir, why you are taking resonance condition, sir? They given XL equal to XC. Okay. Then what is voltage across the capacitor? I naught into XC. Voltage across the capacitor is I naught into XC. The current at resonance condition is 0.5 into XC. What is VC? Voltage across the capacitor 150 volts. 150 by 0.5 equal to XC. Then XC equal to how much you can get? 150 by 0.5 volts. This we can get XC equal to 300 volts. But how to calculate capacitance now? 1 by 2 pi FC equal to 300. From this, what is the C equal to? 1 by 2 pi into frequency 400 Hz. How much C you can get? Come on, do that calculation. Then by simplifying that, we can get C equal to 1.32 microfarad. Is 1.32 microfarad. C equal to 1.32 microfarad. The given options 1.32 microfarad is there. A option and C option. That's why B is not the answer. D is not the answer. Okay. Next, we have to try the calculate one more parameter. We know that at resonance condition, XL equal to XC na. XL equal to XC. Then what is XC? 300. Omega naught into L equal to 300. Then we have to write L equal to 300 by 2 pi F naught. 300 by 2 pi into what is F naught? 400 Hz. Do these calculations, we can get the L equal to S 0.119 Henry. You can do 0.119 Henry. This is L. Then 1.33 microfarad, 0.119 Henry. We are getting option. Which option is going to correct? Option 1. But how to calculate R students? At resonance condition, we know that I naught equal to, at resonance, I naught equal to V by R equivalent. R equivalent. R plus, here two resistances are given. R plus 10. Then what is R plus 10 equal to? 30 by I naught is how much? 0.5. This is equal to 60. Then what is R equal to? 50 ohms we can. So two resistances are there now. That's why I'm adding. Then I naught equal to V by R. I naught equal to V by R equivalent. Then R equal to 50 ohms. That is option A is the right answer. Then apply all the formulas of resonance condition. We are getting the answer. Next. Can you try this? For the circuit shown in figure, the quality factor of the coil is dash. For the circuit shown in figure, what the quality factor of the coil is? For the circuit shown in figure, what is the quality factor of the coil? Simply you can calculate the quality factor of the coil is, generally quality factor is calculated at resonance condition only. The quality factor equal to VC by V. VC by V. The quality factor equal to VC by V. Actually this is 30 volts 50 hertz. Check it is. It's a 30 volts 50 hertz. Okay. Then VC by V. Voltage across the capacitor by supply voltage. What is the voltage across the capacitor? But at resonance condition, quality factor is calculated resonance condition. Then we know that VC equal to VL. This formula is given. What is VL? It is given 40 volts. Then 40 by supply voltage is 30. 40 by 30 volts. They are getting 1.33. Quality factor equal to 1.3. Voltage across the capacitor by supply voltage, but at resonance condition, VC equal to VL. But you have the doubt, sir, how to know this circuit is in resonance condition? Here it is asking quality factor, friends. Quality factor is calculated at resonance condition. Quality factor is calculated at resonance condition. Can you try this? The RLC circuit. The RLC circuit, series circuit composed of components having R equal to 0.2 ohms, L equal to 100 millihenry, C equal to 50 microfarad. C equal to 50 microfarad. Then calculate the resonance frequency. Simple question. I'm leaving homework for you. Just I'm giving the formula. Try it. What is the formula for resonance frequency, friends? The resonance frequency F naught equal to 1 by 2 pi root LC. Try this formula. Substitute LC values. Check the what is the answer you can get. This I'm leaving for you. Do that. But the resonance frequency F naught equal to 1 by root LC. F naught equal to 1 by root LC. Next. A series LCR, that is RLC circuit, has inductance of 10 millihenry and resistance of 2 ohms. At resonance frequency, the maximum instantaneous energy stored in the inductance at resonance. Assume the supply is 230 volts. Assume the supply is 230 volts. Here it is given 10,000 hertz. Yes, friends. You have to calculate what is the maximum instantaneous energy. Maximum instantaneous energy stored. The maximum instantaneous energy stored is half L into Im square. Actually I square, but it is the maximum it is asking, then you have to take half L into Im square. But how to get the maximum value? The maximum current, maximum Im equal to, it is at resonance condition now. At resonance condition, you have to take the root 2 times of I naught. Root 2 times of I naught. That you have to substitute here. What is I naught? I naught equal to V by R at resonance condition. That is 230 by, how much resistance it is given? Resistance is 2 ohms. That is 115 amperes. I naught equal to 150. That is 115 root 2 amperes. Then what is the energy stored? Maximum instantaneous energy. This is equal to half L into inductance is 10 millihenry. Im square 115 root 2 whole square. Can you do this calculation? Half L into L is 10 millihenry. 115 root 2 whole square. How much you can get this? Can anybody? This is the RMS value. This I naught is the RMS value, but it is asking maximum energy. That's why you take the maximum current. Then root 2 I naught. Maximum value if you want root 2 times of RMS value. Then you substitute here, friends. How much you get? Respond. What is your answer? Half L into Im square. Answer. Are you getting answer or not? What is responding? Then by simplifying this, approximately we can get 132.25 joules. 132.25 joules. That is option B is the right answer. A 5 microfarad condenser in the sense capacitor, connected in series with a coil having inductance of 50 millihenry and resistance R at operating at resonance frequency causes a current of 10 milliampere. What the quality factor of the coil? How to calculate what is the quality factor of the coil? It's very simple. What is the formula for quality factor? Once you know the inductance and capacitance values, the quality factor Q equal to 1 by R into students, we know this quality factor equal to 1 by R into square root L by C. This formula all of you all know. Simple formula. How to apply that? That is 1 by R into, here capacitance value is given, inductance is also given, but we don't know about the resistance. Current you know, voltage you know. At resonance condition, we know that R equal to V by I naught. V is 50 volts. V is 50 volts. I naught is 10 milliampere. 10 milliampere. This is equal to 5000. Then you substitute here R equal to 5000 square root L by C. L is 50 millihenry. C is 5 microfarad. L is 50 millihenry. C is 5 microfarad. Now to simplify this approximately how much you get? Quality factor equal to 0.02 we can get. But I already given Q less than 1. Those are called low Q coils. 1 less than Q less than 10. Those are called medium Q coils. Q greater than 10. Those coils are called high Q coils. Please go through the previous explanation. This is 0.02. That's why it is a low Q coil. That is answer is 0.02. It's a low Q coil. That is how to answer. Clear friends? Next. Can you try this? For the circuit shown in figure, what is the voltage across capacitor at resonance condition? For the circuit shown in figure, calculate the voltage across the capacitor at resonance condition. If circuit is missing, this is the given circuit. But the voltage across the capacitor at resonance condition. This is 10 kilo ohms. And this 50 millihenry. 50 millihenry. And this is capacitance is 5 microfarad. 5 micro. The supply is given that 60 cos omega. How to calculate what is the voltage across the capacitor at resonance conditions? Please write. How to calculate what is the voltage? This idea I am giving. Voltage across the capacitor equal to I naught into Xc. You write in terms of angle. That is I naught into, but they not the magnitude. They also consider the angles. I naught into minus Jx. This is equal to I naught into Xc at angle of minus 90. I naught into Xc at angle of minus 90. Then you have to calculate the what is the capacitive reactance and what is I naught. I naught equal to V by R. How to calculate I naught equal to V by R. And you calculate Xc. Xc equal to 1 by 2 pi or 1 by omega c. Xc equal to 1 by omega naught 6. That is how to do the calculations. To apply omega naught equal to 1 by root L. Then you substitute here Xc value. Then omega naught you calculate 1 by root LC. Xc value you have to substitute. Calculate for Vc. Then you can get option C. One more question. A series RLC circuit has a resonant frequency of 50 radians per second and a quality factor of 80. If the impedance at resonance is 10 ohms, then value of R, L, and C is given by. Impedance at resonance is 10 ohms, friends. Then you have to calculate the value of R, L, and C. Simple question. You know resonance frequency. This is the impedance at resonance condition. Impedance at resonance condition means this is the R. Next, we have to calculate the L. Next, we have to calculate the C. Then we can easily calculate. You know the resonance frequency also. Apply the formula of quality factor equal to omega naught into L by R. R you know, Q you know, L you calculate. Apply the formula of Q equal to 1 by omega naught C into R. R you know, Q you know, omega naught you know, you calculate the C. Clear? From that you have to calculate the what? Simple question. Calculate the RLC values. This also I am giving. Just idea I am giving. Please try by your own. Practicing the questions is important in network theory. A series RLC circuit has bandwidth of 20 radians per second and resonance frequency of 1 kiloradians per second. If R equal to 10 ohms, R equal to 10 ohms, then what are the values of inductance and capacitance respectively? What are the values of inductance and capacitance respectively, students? Bandwidth is given and the resistance is also given. Simple. You have to calculate. Yes, bandwidth equal to R by L formula. From this L equal to R by bandwidth. Resistance is 10 ohms. Bandwidth is 20 radian per second. How much resistance? How much inductance we can get? 0.5 Henry. Inductance is 0.5 Henry. The given options only option D is there. 0.5 Henry. Then how to calculate capacitance? How to calculate the capacitance? Omega naught square equal to 1 by LC. Yes, right. Omega naught square equal to 1 by LC. From this, C equal to 1 by L into omega naught square. 1 by L into 0.5 into omega naught square. Omega naught is the 20. That is 20 square. By simplifying this, we can get the 2 microfarad we can get. We can get 2 microfarad. C equal to how much we can get? 2 microfarad. The value of capacitance C equal to microfarad. That is option D is the right answer. Okay, this is about the detailed discussion of different concepts of series resonance. That is resonance in series circuits is completed. Then in resonance concept, last concept is resonance in parallel circuit. Tomorrow it will be complete, friends. Tomorrow session I will complete this topic. Then I will start the coupled circuits. Then after completing coupled circuits, next to three important topics in network theory: theorems, transients, and two-port networks. Theorems, transients, and two-port networks. Thank you. I'm ending the session. Please refer this PPT in my Telegram chat. I will share the total resonance, series resonance, whatever up to now it is completed now. This total PPT I am sharing in my Telegram chat. Thank you. Any doubt? Maybe my classes are going very slow because for timing I am taking very less number of hours. But I will try to give the maximum information. Thank you very much.